Greetings, Graham Warren again, looking at some queuing analysis with you for the Antico Caffe Greco case. So we're in the case study right now. Just want to point out where some key information resides. This guy here, let me see if we can change the color of that. Probably can't. Yeah, maybe I can. Make it a red. So this is the 29 per hour arrival rate. So we're going to refer to that as lambda. That's if they operate independently. If they're working as a pool of baristas, serving some portion of the overall arrival load, then they're potentially facing 205 customers per hour or some fraction of that. However, you're parceling up if that's what you're doing, the arrivals. The other key information here is that if you're working with a clover, which is the base case, mean processing time is 60 seconds with a standard deviation of 10 seconds. Now, if they switch out that clover and they go with a valve, let's just clear this out, then that mean stays the same, but they're dropping it, well, the standard deviation worsens to 30. Let's see if we can just find that number for you. Probably down here someplace. Yeah, so if they're untrained, baristas on the valves would have a 30-second standard deviation, but if they do get the advanced training, then that improves to 15 seconds. So 10 for the clover, whether they're trained or not, 30 for an untrained barista on the valve, 15 seconds standard deviation if they're trained on the valve. Okay, this is a picture of a valve. All right, so want to run through a bunch of scenarios with you. Going to demonstrate pretty much how to analyze different scenarios rather than specifics that are going to, close down or drive toward a final solution. So let's get going. Let's look at the base case. So I'm looking at these different calculators. I really just need the GGK calculator. And the main reason for that is we've got a standard deviation associated with the service times, whether it's clover or a valve. We're needing a general time distribution. So the MMK and the MD1 would be conservative estimates of, well, the MMK would be a conservative estimate because the service time distributions are not exponential. So this is the one we're going to go with right here. Just click on that. And here we go. So just a word about where this code sits. It sits in Python, sits on Hugging Face. We're getting a freebie here. So it may show up as needing to be restarted, and that just is because they're not providing the compute, forever and ever. They do shut down the space if nobody's using it. So be prepared to have to restart it and wait a few minutes, but hopefully you're going to encounter it in this state. So once we've started it, it should be running for pretty much the duration of the case, but somebody may have to kick it off to get us started. All right, so let's think about our base case. I will try and annotate this. See if I'll get my pen back here. So this is my base case. All right, and okay, so base. All right, so I'm going to independent baristas, and they're each facing a load of 29 customers per hour. They're using the clover, and that's uniformly true. And so the mean time is 60 seconds. And the standard deviation of their service times will be 10 seconds. Okay, so we can fill in most of this information. Now, just to calculate the CV sub p squared, The way we get this, the formula is, messed that up, but this is a CV sub P squared, so the coefficient of variation squared for the processor, and you take the standard deviation over the mean, and so it's going to be 10 over 60, because standard deviation is 10, mean is 60. I want to square this, running through this through the calculator, and I'm getting 0.0 0.027 recurring. So we'll probably just call that 0.0278 or something. All right, so let's go ahead and plug this in and see what we get. So again, we're analyzing, in fact, just a single barista now, because they're all identical essentially. They have equivalent training more or less. So from the perspective of the analysis, we can treat them as statistically indistinguishable. So let's analyze one of them, and then the performance of that one would be the same across the board. Now, for a Poisson arrival process, and we are assuming that these arrivals are Poisson, the standard squared coefficient of variation is 1. That's just true for a Poisson process. The standard deviation and the mean of this process, or of the interarrival times, are identical. So that's just 1. Now, we do need to plug in a service rate here, and they are serving, because the mean service time is 60 seconds, you're doing 1 per minute. Basically, the machine's doing 1 per minute, and that 1 per minute then is equivalent to 60 per hour. The squared coefficient of variation of these service times is unitless. And so you can do this either in seconds or minutes or hours, doesn't matter. We've already calculated this number, and it's the standard deviation divided by the mean. So I'm just going to plug it in as 0.0278. You could put this in as 0.028 or put a bunch of sevens in there, up to you. And we have just one server. So this is sort of how we will treat it if we're not, how we will treat the analysis. We're going to look at each independent barista sort of separately, analyze them, and then we'll have that person's performance, and every barista then would be statistically equivalent to that barista that we've analyzed, and we have our scenario analyzed essentially. All right, so go ahead and hit submit. And this is what we're learning here. So going to just write this down with you. So the key numbers that I have here are, just get my pen back, is this number here. So this is a 48%, 48.33, but I'm just gonna, say for approximately 48%. Another key quantity is time that people spend in the system. Now this is in hours. So 0.0247 times 60. So that would be this is in hours. So yeah, I multiply that by 60 to get the number of minutes. So it's 1.482 minutes. So I want to just make a note of this. On records, just so that I can talk you through the comparison, at least for the scenarios that we're considering. Okay, so this is our base case. And sort of analytically, what we're going to do is look for improvements relative to the base case. There's no sense of reaching maybe within the parameters as spelled out of the case. You could argue that you have the truly optimal solution, but this is a business, right? So there's an endless number of possibilities. So there's no real hope of securing what is sort of the ultimate optimized solution for a cafe like this. So the key will be establish the base case, and that sort of pegs where you are currently. And then if you do find scenarios that are better, they become sort of the new standard or the recommended alternative, and you can sort of step through argumentatively a bunch of scenarios and then hopefully pitch the one that has superior performance and that is the best reward, but also factors all the risk criteria, because you may find one that sort of like really out on a twig someplace, and it may look good if conditions don't vary a lot, but you have potential for variation in the traffic levels here. So then the question would be, how does a situation or a solution like that hold up? All right, let's not get too far ahead of ourselves. Just going to try and look at a number of options here to show you how the queuing models can be used to analyze scenarios in the ACG setting. I'll just go ahead and clear what we have here. And the next, or sort of the first non-base case scenario that I want to consider is I want to take out the clover, keep everything else the same. There's no pooling, there's no training, just going to switch out the clovers for valves across the board. The valves, I've got that sort of wow, that antique look and feel, but they do come with performance downgrades in the form of not the mean, but the standard deviation increasing from 10 seconds to 30 seconds per coffee. So we know that variance hurts. The question is, how much if we did do a makeover here with all these machines. Okay, so to get this to go, I just annotate this again. With an unfamiliar tablet here, which is why I'm struggling just a tad to get this thing to fly. Okay, so so the next the scenario here involves clovers pivoting to valves. These are the Victoria Arduino Venus models, 17 to $25,000 roughly. The clovers are about an 11K machine. They clover verticas, as commonly used at Starbucks. These valves are sort of some luxury item beyond that. Okay, so what is needed here? The mean stays the same. So there's nothing that we're doing to the load that each barista faces. They're seeing 29 customers an hour coming at them in a Poisson process. So these here remain the same. And there's still one server. The mean stays the same. So it's this guy here that needs help. So this CV sub P squared is now going to be the standard deviation, which is 30 seconds. We're assuming these baristas are untrained. We haven't given them any help on that front. So 30 over 60 squared, it's a half. And so this should come out at a quarter. All right, so let's go ahead and change that. Go ahead and hit go. So what you'll notice is that the standard deviation remains at 48%. The variance is not changing the utilization. So here we have the same approximately 48%. Every barista is roughly only busy half the day, a little less than half the day, 48.33% of the day. So you're probably overpaying. So one of the thoughts that crops up here is like, okay, so can I help myself out by maybe firing one of these people, or when they do leave, to just not replace them, something along those lines. But you have too many most likely. So that's something that you could pursue. And then this W sub S number is again expressed in hours. So let's see if we can get that converted for you. So the variance is increased, right, from 10 seconds to 30 seconds because of the machine switch. But what does this look like on the ground? So 0.0264 times 60. All right, so now you're at, check that, 0.0264 times 60. All right, so previously we had 1.482 minutes average waiting time from the time you place the order to time you receive the order. Now you're looking at 1.584 minutes. So, you make the call. Apparently not all that big a difference. 1.48 is increased to 1.584. exactly how many seconds that is, but you make the call. All right, so that's the first scenario that we've analyzed. I'm going to just make a note of the time here again for my own purposes. Right, so what I want to do now is consider, okay, so we've changed the valves, changed the clovers for the valves. Want to look into this possibility of, okay, so what if I get the training as well as the valves for, for every barista across the board? So now the only thing that changes relative to what we've just analyzed is standard deviations going from 30 to 15 because they're sort of, staying in their lane. They kind of know how to operate their environment and these machines better because they're being professionalized through this additional training. Training runs 29.95. That's in euros. It's offsite. It's 100 hours spread over something like 15 weeks. You can read the details in the case. And ACG has to pick up the tab on that, but they do not have to pay the baristas who are basically picking up a professional credential and are there sort of on an unpaid basis. They're volunteering to do the training, essentially from their perspective. All right, so the only thing that happens now is instead of having this, so I'm doing plus the training now. So what happens is this guy here becomes 15 because guess what, they're trained. All right, so this is now a quarter squared. Okay, and so this is 0.25, and so 0.0625. In other words, this is 16th. All right, so let's plug it in. 0.0625. All right, so notice again that nothing changed with the utilization. They're all on average working less than half the day, 48.33% of the day. But this now has changed. It's now 0.0249. So what we're expecting to see is a number between 1.482 and 1.584. Those were the numbers for the clovers and the valves with the untrained baristas. Here, you're at 1.494 minutes. So just a few seconds longer than the clover. It's a nominal increase from 10 seconds to 15 seconds for the standard deviation. And on the ground, the customers are your call, but maybe not feeling as much pain as you might think. Okay, so we've got three scenarios set up here. Want to try something a little different now. Let's go ahead and clear all this out. I want to go back to our base case and say, all right, let's just go back to our clovers, and we're going to fire one of the baristas or have them find them some other role. Okay, so the scenario now is base case -1 barista. So now we've got 6. All right, so now the way that we think about this is the overall, the arrival rate overall per barista. Overall, it's 205 per hour, right? Now, instead of 7 people, fielding these service requests, now you've got 6. So when we divided by 7 originally, we got 29 per hour, but now we have to field that, the customers are still going to come. It's just that now you only have 6 people to service them. So 205 divided by 6 is 34.16, let's say 7. It's actually 0.16 recurring. That's fine. So let's think about how we're going to analyze this. So what I do need to do is I'm going to change my arrival rate accordingly. So it goes up. So what we're thinking is going to happen here is utilization is going to go up because now I have to do the work of seven using only six people. Machines are the clubbers, relatively low variance there. Standard deviation is only 10 seconds. And yeah, let's see what we get. So we've changed that because it's a Poisson process. The squared coefficient of variation for arrivals remains 1. The service rate is 60 per hour because we're back with a clubber. In fact, for the VAV and the clubber, it's always 60 per hour. And then this one is back to the 10 divided by 60 squared. So just forget what that number is. But it's, yeah, 0.027. 0.278. So this was that original base case squared coefficient of variation CV sub p squared. Go ahead and run this. And you see here is, as we might have expected, now your rounds up a little bit. So now your baristas are 56.95% utilized, about approximately 57% utilized. So you're getting better bang for your buck. You let one of them go, you're saving that salary, still serving the same number of customers. From a profit perspective, it's a better deal. Now, you're going to have to think about, we're just exploring a reduction of one. You could explore going down to 5, to 4, to 3. It's your call where you want to go analytically. At some point, utilization is going to get up into regions that is going to challenge their ability to stay in the job. There are some references in the paper that look at mental health and suicidal ideation, for food service workers. So you definitely want to stay away from sort of the workload levels that would start to threaten your the sustainability of your operation. Okay, so question is, with Fighter Barista saving the money, they're working more. How does this play out on the CX front? So 0.308 times 60 is 1.848 minutes. So definitely, more than the base case, which is 1.482 minutes, more than the VAVs with the training, which was just the VAVs alone without trained baristas, which is 1.584. We're getting up there now, but still less than 2 minutes. You make a call as to whether this is going to be acceptable. And when you do the analysis with the queuing, all we're able to extract from this queuing calculator is the mean waiting time, or time in system from the time from placing the order to receiving the caffeinated beverage. If we want the distribution of those waiting times, we will need to use the AnyLogic model. Get a histogram, which we're just going to eyeball pretty informally, but can't get that distribution out of queuing. I have to go to the simulation to get that. We'll look at that in another clip. All right, so we've got the base case minus one barista analyzed. So that's interesting because it is a savings and maybe not all that impactful from the perspective of the customer. All right, let's have look at another scenario here. I'm not pursuing these, intentionally not pursuing them, perhaps in the directions that you want me to go. Rather, this is a demonstration of, how to do this rather than to try and, drive to a final solution here. So the next thing I want to look at is base case, but instead of having the baristas operate independently, we're going to pool the orders. So let me write this out. So this is pooling as only change. All right, so now what we're going to do is this one's going to become 205. This remains the same. This remains the same. We're working with clovers, right? Oops. On the previous one, I seem to have screwed this up. So let me just fix that. 0.00278. Okay, so the impact was not even as much as we were saying. Let's just see what it is. So that was the six barista, the base case, but losing one barista. So it was actually only 1.68 minutes. I think I had you down there for not 1.8 or something, but it's only 1.68. Okay, but now what we want to do is we want to go to 205 here. Okay, because essentially what we're doing, just to visualize this, is we're pulling all of these orders, all of these customers sort of get funneled into this centralized order queue. So this is 205 per hour. And then you have your, how many you got there? Seven baristas. Okay, some of them are not so smiley. And they're serving. So the impact here, once I run this, chance to get my stuff together here. Oh, I have to change this. We have, in the base case, 7 baristas. So this is that original setting, just pulling the orders instead of having them operate independently. The reason I know I screwed up there was I saw the utilization jumped above 1, so I knew there was something bad. And what I didn't factor here was exactly this issue, the 7 baristas. Okay, so let's try this again. Okay, there you go. Now, maybe this is an interesting result to you. What you notice here is you're back to, the 48% setup. Okay. I think originally it was like 48.33. Actually, it should be the same decimal numbers here. When we analyzed the single independent barista, we had an arrival rate of 29. If you multiply 29 by 7, I think you get 104, 204, not 205. So that's a small approximation there, in the base case. But we're getting a number that we're roughly expecting here of about 48, 49%. Key is what's happening to our payment system. So here, 0.0169 times 60, getting 1.014 minutes. All right, so this is an important result, and that's quite surprising to many people, how powerful this pooling idea is. So definitely something to consider because it's low cost. You've got some sort of software system already that allows you to have folks scan their QR codes, enter orders on an app. So it probably is not a lot of additional functionality to create a central order queue that baristas pull orders off of and serve. So pooling looks like quite a big winner. Now you can argue that going down in the base case of 1.482 down to 1.014 is not such a big deal. But as you, let's say you take the base case and, we considered going down from 7 to 6 baristas, and you could look at going down to 5, 4, maybe 3. As you decrease the number of baristas, you can expect their pain, the pain of the remaining baristas to rise, and their utilizations are going up. But also, waiting times are going to blow up, right? So you may want to do a mix of these things where, there's the training option, there's the valves, there's pooling, there's changing the number of baristas. These are all options you can explore. So I think I'm going to do just a couple more with you just to see where this goes. This would, pretty much any of these would be viable solutions apparently. But let's take this one. We've got pooling in place, and let's not have this the only change. Let's also go to 6 baristas and 6 baristas. And it's as simple as this. to analyze this. So I have to change this guy to 6 now. So essentially what we do is we've just got hit go here. And if you scrub one of these baristas, and so now you're at 56.94%, and you're no longer at just about a minute. You're at 0.0174 times 60. Now you're at, is that right? 0.0174 times 60. Wow, the needle's hardly moved. 1.044. So this is this is something to get you thinking, because you are paying one less salary, right? So serving the same number of clients, so profit's going to be higher. It's hardly moved the needle on the CX front. Now, again, all we're looking at is the average waiting time in system. You may want to look at the histogram for your proposed final solution. So maybe run the simulation model only once you've sort of like settled your differences with all these different scenarios and finalize your recommendation, or think you finalized it, and then so run it and then just see what the worst case looks like, because it is possible that those worst case service times, the mean may be a minute, but worst case could be 5-10 minutes, and it's those. If everybody else is getting their coffee in a minute and you're waiting 10, the anger level rises, and you start looking at your TripAdvisor app to express your appreciation for what's happening. All right, so want to just think about one or two more scenarios with you. So you got these various options: changing the number of baristas, pooling, having the folks switch them to VAVs or not, getting them trained or not. The training doesn't really make a difference on the performance from the performance perspective. If they're using the clovers, but sort of their overall ability to present, their leadership level would potentially still be something you'd want. So that's just something for you to think about. You've got this presumably relatively upscale environment. Is it important to have all the baristas trained to this high level? So it's a call for you to make. All right, so I want to just think about one complex scenario that we actually can't really analyze directly using the queuing models, but that we can analyze using the simulation model. So I just want to go ahead and clear up what we have here. Suppose you decide that you'd like to analyze this setting here. You want to do 3 clovers and you want to do 3 VAVs. And you're going to get training only for those baristas. So here's no training. You can't analyze this directly using the queuing model. What you could do is you could think about these folks here as being pooled. And this is actually another choice. You could analyze them sort of independently, where you treat them each as having an arrival rate of 29, the appropriate standard deviation for their machine, and then and also training level, and analyze how that looks. But what you'd end up getting is, if you treat them all independently, you'd have all the Clover baristas would have the same performance, and the VAV folks would have slightly inferior waiting times. Their utilizations are going to be the same, about 50-some%, 56-some%. And what you could do is you could do sort of like an average of the scores here. So quickly explore how this weighted mix would go. So I'm going to analyze them as if they're independent. So here it would be 29 across the board. So this is for a clover now, because this is 10 divided by 60 squared, right? Standard deviation if they're using the clover. whether the training or not is 10 seconds. And so we run this, and so you see that utilizations are as I reported. So 48%, 48.3%. And then I'm just going to write the number down here. So this is this is row 0247. And then for the other guys, you might remember it would be 0.25, right? 30 divided by 60, that's a half. Square that becomes 0.25. Run that. These are numbers we've seen previously. Just trying to make the point that you could come up with some weighted average here. Again, this is remains the same, but this is now 0.0264. Get an average and report that. You're able to get the distribution and a better estimate for this blended scenario where you have different types of machines. Just one thing to think about here. I mean, the numbers are so nominal here. 0247, the difference is at least, and 0264. You know, this is worse because you're using the valves, but whether or not the customer notices is another issue. If there were material differences in the performances, you know, in the time to get a coffee using a clover or a valve, what you may find is that some customers then jockey. They switch over from maybe showing up in an area of the restaurant typically served by a valve, but then deciding after they sat around for a couple of minutes, hey, you know, folks over there are getting served using clovers. I'm happy with a clover. Let's go for it. So that pivoting, that jockeying behavior probably not going to happen here because it's almost indistinguishable waiting times in systems. So, but I just mentioned that you know that could crop up in other situations where the time to get service differs materially. Alrighty, so I think you've got sort of an outline of how to analyze these different levers that you can pull in this operational design setting. I think there's work to be done outside of just the queuing analysis. The psychology matters concern of Carlo remains, and you know there could be other moves. You know, it's a real world out there. So if you have other suggestions for how to set this operation up, we're all looking for you to at least do some queuing analysis because that's sort of the analytical backbone in this case. But looking to see what ideas you have and how you're going to help Carlo. Enjoy.